Hi, Mike Mays here. This is another video about Scratch and mathematics, and it is drawn from ideas in this upcoming book, Math Hacks for Scratch, that No Starch Press will be publishing in 2024. It is full of ideas that you can use Scratch to explore math, and you can use math to make Scratch more efficient, to answer questions that otherwise would be out of reach. So I'm going to talk today about a topic in number theory. Number theory is mainly in chapters 2 and 3 of this book, but there's a particular idea about number theory that has a nice little program that you can use to start with. It is about using number theory to explore prime numbers, whether a number is prime or not. So we're going to come up with a test for primality and then use that. So let's get started in Scratch to make that happen. It's going to be a program that is about calculating prime or finding out if a number is prime or not. So I'll do that with a custom block. I could do it with a little program and have Scratch-Cat prompt for a number and then do the test, but maybe it makes as much sense to think about this as a tool for later exploring, and a custom block that you could export and then import into another program that you're working with would make some sense to have as a tool. So the block that I'll make is called prime. And Scratch is pretty generous about how it lets you name things. I'll put prime with a question mark to remind me that this thing is for finding, asking if a number is prime or not. And the number that I'm going to test, I'll call n. So there's the custom block, and now I'll get to define the thing. So the way I'll do it is, for the custom block, I will have it pass a value back that is related to the name of the block. So besides this custom block name, I'll make a variable that has the same name, prime, even with the question mark, and start by setting prime to be true. I'll think of it as a Boolean variable, true or false, and I'm interested in finding out if the number's prime or not. That would be true if it's prime, and I'll start with that and then try to disprove that, try to find reasons that it would be false. So I'm going to do that by trial division. So one more variable, I'll put in trial to remind myself I'm doing trial division, and the first number I'll try to divide by is 2. So I'll set trial to 2. So the first thing I do is check to see if n is divisible by 2 or not. And if it is, then it's not a prime number. Good. Bigger than 2, not a prime number. So that's what I want to have happen. But now I'm going to try, if 2, it's not divisible by 2, then I want to try 3 and 4 and 5 and so on up. So I'm going to do the rest of the tests in a loop. So it can be a repeat block. I will repeat until condition is satisfied. And one way the condition could be satisfied is if I end up doing a trial division that is bigger than some value. Now you can think about how big that has to be, and here's a place to be very efficient. If a number is prime, then it has a factorization, a product of 2 factors, so they could both be the same size, like the square root, or if one of them is bigger than the square root, then the other one has to be smaller than the square root. So that if I've done tests up to the square root, I will have picked up every case that is with one of the factors less than the square root to find that the way the number factors, I've got one of the factors, and it's enough to show that it's not prime if I found a factor of the number up to the square root. So one test I can put in is I can stop doing my work if the trial divisor is bigger than the square root of n, the number I'm testing. The square root of n. And the other way that there's no reason to keep going once I've shown that the number is not prime. So the other possibility would be is if prime is false. So either of those conditions would be enough to stop the loop. Either of those conditions would be enough to know that the number is not a prime. And now we're going to go through and test do the trial division steps. And that's another loop. It'll be an if loop. And here's the test for the divisibility. If we want to use the modular thing, if n mod trial is 0, that means that n is divisible by trial, and we found a trial, we found a divisor. And if that happens, then we will know and we'll set prime to be false. And then after we tried that trial division, we'll add 1 to get the next thing to check. So change trial by 1 to get up to the next one. And that's all we need. So we don't really need to keep track of this trial division. Let me not show that. I'll click that off so it doesn't show in the window. And now bring this over and just try some values out. Let's check to see if 7 is a prime. I'll click here, and here's what the value of that variable turns out to be. Is 7 a prime? Sure enough, it is. Is 10 a prime? Try that one. Well, it better not be. So out comes false. So we get true and false depending on what happens for. We can test numbers that up to pretty big. Let's check 1001. That's not a prime. That looked like it might have been, but it's not. Maybe it would be worth putting in an extra little step in here so I could see if a number's not prime, what it's divisible by, and that wouldn't be too hard to do. Let's put in one more variable. Let's make it divisor. And when I found a counterexample from this n mod trial equals 0, when I know that n is not a prime, so that the question is false, then we'll set divisor equal to that trial value. So with that in there, now when I check, so now I've got divisor showing, and when I check prime 1001, oh, it's divisible by 7. And I guess once I knew that, I could have figured that out. Okay. Well, now I have in mind using this to explore an idea, something that people kind of get wrong, and it comes from a basic theorem in number theory about how many prime numbers there can be. And this is something that Euclid figured out more than 2,000 years ago. Euclid realized that there are infinitely many primes. You can never be done listing all the primes. And it's a very easy proof. If you think you've got all the primes, put them in a list. list all the primes that there are. If there's only finitely many, that list is done. You've got them, and that's the end. So with that list, multiply all those numbers together and add 1 to it. That product of all the primes that exist plus 1. Well, what kind of a number could it be? Well, it can't be divisible by any of those primes in the list because it has a remainder of 1. That plus 1 means that it's not divisible by any of those primes. So either it's a prime itself, or it's divisible by some primes that didn't make the list. Whatever prime divisors it has weren't on the list, and that means that the list that we said we had, the list of all the primes in that finite list, was wrong, was not complete. There are primes that aren't on that list. Any finite list of primes that you give has within it a recipe for building a new prime, and that means you can never be done. That's why there are infinitely many primes. But what's interesting about this theorem is what it doesn't say as much as what it says. You think about it, well, it's sort of like a good way to make up primes, like a rule to generate primes, is to multiply and add 1. And it would be nice if every time you did that, you got a new prime. So let's just check that out. Back to Scratch, and I'm going to think about this business of multiplying and adding 1. So let's multiply some primes together. Let's multiply 2 times 3 times 5 equals 30, and add 1 to that, 31. So is 31 a prime? Well, let's see, prime 31. It is. Two times 3 times 5, that was, times 7. 210 plus 1 is 211. Is 211 a prime? It is. 2 times 3 times 5 times 7 times 11. 2310. Add 1 to that. Two, 3, 1, 1. Is that a prime? True, it is. We're on a roll here. One more step through. 2 times 3 times 5 times 7 times 11, that was that number, times 13. 30,030. Add 1 to that. $30,031. Is that a prime? False. And in fact, now it's reported what the divisor should be. It happens to be divisible by 59. And 59 is not any of the primes in that finite list, 2, 3, 5, 7, 11, 13. But that product plus 1 has in it room for a different prime in its factorization. So this is a tool, and here's a thing to explore in math that the tool is good for. We do a lot more in the book talking about having figured out how to find a prime factor. We can find all the prime factors and write down the actual way to write any number as a product of primes. It's a unique way to do that. But that's for another day. This is a little primality testing exercise in Scratch. Hope you enjoyed it. See you another time. Bye-bye.